Hello, this is a project dedicated to the class of actuators and developed by Christian, Alberto, Paul, Erasmo, and Eric, which consists of controlling the speed of a DC motor with rectifiers in a half-wave configuration.
Some DC motors cannot be fed by a common voltage source because these consume high current, which cannot be supplied. The option which we have is to use the AC power supply to achieve to get that excessive current. However, this voltage must be converted into direct current to be supplied to the DC motor.
Later, we will explain in detail some parts of the project itself. The idea at the beginning was to do everything through a DAC and with the help of LabVIEW, but at the end, it was decided to use it so to know the speed of the motor and then control it from an Arduino program.
Description of the solution. The solution is to apply electronics to control the waves of the current and voltage. In our case, we're going to use AC voltage to use it in DC motors that requires a lot of current using SCR. This is to avoid the use of an extra current supply. Also, we are going to use it to control the speed of the motors using the input signal gate of the SCR. Theoretical framework. A semiconverter uses two diodes and two thyristors, and there is a limited control over the level of DC output voltage. A thyristor is normally a 4-layer 3-terminal device. 4 layers are formed by alternating N-type and P-type semiconductor material. As you can see, there is a wave of the output signal of the SCR that we are looking for.
Semiconverter configuration. These controlled rectifiers are used to control the intensity of some things using alternative current, like the light of a spotlight or the speed of a motor. In this case, we use it to control the speed of a DC motor. The characteristics are the following. It has only one polarity output, voltage and current. It only controls half of the wave from 0 to 180 degrees. We need to use two SCRs and two diodes connected in a bridge configuration. There are times in which our output voltage will be 0, so that is why we also need to set a free wheel diode, so when we don't have voltage we can have current and make the motor work all the time. We will fire the thyristors from our Arduino, which detects the zero crossing, and the program of the Arduino will help us to move this fire angle so we can control the speed of the DC motor. Zero crossing detector. In alternating current, the zero crossing is the instantaneous point at which there is no voltage present. In a sine wave or other simple waveform, this normally occurs twice during each cycle. To create this zero crossing detector, we use a full wave rectifier and an optocoupler which has a light emitting diode and a phototransistor. When the voltage is zero, the diode goes off and the optocoupler transistor stops working, and the leg where the transistor collector goes is raised to 5 volts thanks to a pull-up resistor. And when the input voltage is other than 0, the transistor works and sends that leg to 0 volts. This voltage is the one that we will send to the Arduino to later on send it to the SSRs.
Then we have our Arduino program. First of all, we start with the reading the signal of the zero crossing detector in an analog input in Arduino. Then it reads the value that the potentiometer sent in other analog input. The value is between 0 to 1023. Then Arduino converts the number that the potentiometer sent from 0 to 6. This value is for the delay in milliseconds. Then Arduino converts the value of the zero crossing detector, and if it is equal or greater than 511, it applies a delay between 0 to 6 milliseconds. Then it sends a pulse of 1 millisecond and repeat the cycle, but if this false, the cycle is repeated again.
The program consists in acquiring dynamic data from the DAC assistant, and then this dynamic data transform it to a waveform. Then this waveform we send it to a graph so we can see how the voltage we are measuring behaves, and this same waveform we send it to a function call it extract single tone information, and this function give us the detected frequency, and this frequency we send it to a sheet register that will give us 10 numbers, and these 10 numbers we send it to an array of sums that will sum us all these 10 uh, data numbers that we send every while, and then this sum we divide it into 10 so we can have an average value and the result can be more exact. Then we send this division to a multiplication by 60 so we can get our RPM, and this multiplication we send it to a division over 1000 so we can get a value more small because the RPM is a result normally above of the 1000, and these results we send it to a gauge and also to a numeric indicator so we can see in our front panel how the how much the speed of the motor is.
Then we have our block diagram. We start with the AC voltage. We have 127 volts for the input, and we transform to 24 volts. This signal is divided into parts. The first part is for the semiconverter configuration, and the second part is for the zero crossing detector. This circuit sends a signal to Arduino and is compared to send a pulse to the semiconverter configuration. It's like a tiger, and this this action is our firing angle. With this signal, we can um, manipulate the signal and the torque and the speed of the motor. Then, with a sensor of optocoupler, we can calculate the speed of the motor with the help of the LabVIEW and the data acquisition system. This data is compared in our computer for the user. About the part list required, we need a thyristor SCR 2N6397, a DC motor, two diodes MR745, two resistors of 220 ohms, an optocoupler 4N25, a phenolic board, a lab DAC and workstation, an Arduino Uno, a chassis, soldering iron, wire, screw terminals, and voltage source of 5 volts.
So for our project, we made a box in which in the left side we put a switch that turn it on and off the circuit, and in front of the box we put connections that are for the motor and connections that are for the Arduino, the DAC, and for the voltage of the transformers. So we made a program in LabVIEW that in which we have a speedometer and we can see the what velocity have the motor. So we use a potentiometer and with this we can control the velocity of the motor. So the potentiometer is in front of the box so we can move easily. And inside of the box we can see the all the circuit, the transformers, and the Arduino.